wrong. You do not have that much. You do not have that much symmetry. Maybe you have only 3 coordinate covariance only. So how to see that? How to see that is look at the sympathetic potential. Now the important, let me talk about philosophy. There's a very important philosophical problem concerning Hamiltonian formalism. In Lagrangian formalism, it's very easy to talk about symmetry by Lorentz theorem. But in Hamiltonian, the most important advantage of Hamiltonian is to tell you who are the kinematic variables. They define the kinematic variable. You have to define the kinematic variable or the dynamical degree of freedom, and then the rest is to put in the potential. So that means, first of all, you have to choose what are your corresponding P and Q here. The choice of P and Q is to define the kinematic of the theory. Once the kinematic of the theory is defined, then the rest is to put in different potential. Will give you different Hamiltonian, give you different evolution. So this is the important point of Hamiltonian formalism or canonical formalism. The canonical formalism is, let me repeat once again, is to provide a tool, for example in this case the sympathetic potential P and Q, to tell you this guy Qij is canonical conjugate to Πij, and Πij is canonical conjugate to Qij. These are the canonical pair or the function in phase space that form the Hamiltonian. These are the kinematic pair. Now, the important observation is this kinematic pair actually can be decomposed into the bar variable and the Q bar variable. I didn't write down what's Q bar. Anyway, the bar variable means transverse. Means traceless, and the Q bar variable means unimodular. It means the determinant of Q bar is equal to 1. And then you subtract off, then this is algebraic identity. This is algebraic identity. You can prove it. You don't believe me. So this sympathetic potential can be decomposed into 2 parts which are orthogonal to each other, namely the bar part and the trace where pi is the trace of bar triple. Trace means that Qij contract with bar triple. This is the trace, and then this is log Q. This log Q to the third. Q log Q is the log of the Q. Okay. Q is the determinant of Qij. That means Qij can always forget what 1/6 is Q bar. Okay. So determinant, that means determinant of Qij is equal to Q, and then determinant of Q bar Ij is equal to 1. This is what this decomposition means. Okay. Now, the important point is this decomposition is orthogonal. That means there's no mixing term between pi and bar variable. This is important. There's no mixing between bar variable and unbar variables. Now, more important is this object delta log Qi is a 3-dimensional diffeomorphism scalar under diffeomorphism transformation. This transform as a scalar. Well, this is technical. This is technical important. This is it means a scalar. It means a coordinate independent. This transform as a scalar. So that means if I identify this as my time, then this will be my corresponding. This will be my corresponding energy. For example, x dot t that is equal to what? Xi dot pi and then minus e dot t, right? So if I identify, so the coefficient of t is identified as energy. So so if I identify this as my time variable, then this will be my energy variable. And then this time variable is not given by the background. It is constructed out of the spatial matrix. It's not come from nowhere. It's construct. It's not given to you. You can given any matrix, you can construct it. You can calculate the determinant of that matrix, and then take a logarithm, and this will be your time variable. So we call it intrinsic time. So if you do that, that means, okay, now you combine 3 and 4. You combine 3 and 4. That means there's no time symmetry in your field, in 4-coordinate symmetry. Then you ask, what is the corresponding time? There's no coordinate time. We argue. But however, intrinsically from your matrix, you can construct a time out of it, which is a 3-dimensional diffeomorphism scalar under coordinate transformation. So if it becomes a constant, that means it is a gauge invariant object.
So how do you choose I and J to start with? How do you choose the spatial coordinates to start with?
You mean here?
You want to use the spatial coordinates, take a determinant to define your time, but
yes.
How do you define spatial coordinates?
No. The problem is like this. If you're doing numerical gravity, then you know, okay, I have 2 black holes, and I release them and see how these black holes collide, right? Okay, that means I've given you a matrix, Qij.
I will get Q mu nu to start with.
No, this is not correct. No. If you are doing numerical simulation, okay, that means if you want to see the physics of 2 neutron stars, what that means? Okay, I construct the matrix of 2 neutron stars, right? Which I given to you. That's I hand to you Qij and pi ij as my initial data, and then you evoke this data. Suppose you have Hamilton, evoke this data, and then after hours and hours of computing, then you see, oh, these collide together to form either 4 black hole or 2 neutron stars, blah blah blah, things like that. This is given to you. Okay. That means given to you any initial data, given to you any configuration, then I can construct out of this configuration an intrinsic time variable. And then I can vary things according to this variable. Okay, this has been used the very spirit of canonical formalism. In canonical formalism, you don't need to have a time. I mean, just a relation between evolution. I mean, change of relation with respect to each other. Okay, so from now on, I will say, well, my change with respect to this object, which is extract from the which is given to you, and the problem given to you, or the problem given to God. For example, if God wants to create this universe, he has to have something to begin with. From that something he can construct. It's the spatial matrix. From that he can construct a intrinsic time, and then evoke everything with respect to the intrinsic time. This is the idea. Okay. So actually, I'm seriously run out of time, but anyway. Well, if you don't believe me, you ask this question. I don't understand. I ask almost every cosmology people in Yokawa Institute or in Spain and everywhere. ask why Hubble constant is physical, or why cosmological constant is physical. For example, constant free curvature is physical. Nobody give me an answer. I also asked this to Robert Roth in Chicago. And they say, oh, blah, 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 blah. They didn't really understand. Well, the fact that Hubble constant is physical, that means what? You see, Hubble constant is time-dependent object. That means for coordinate covariance, if a die-hard general relativity believer, then this cannot be physical object because this depends on time. I mean, this depends on coordinate. I mean, I do a coordinate change, this will change. This cannot be a what? Cannot be a physical object. So the cosmological principle depends on how you slide the space into constant field curvature. But it's physical. But you know, in Hilbert Einstein, this is physical, but not the field curvature. But why cosmological principle physical? Why it's workable? Why the MRW cosmology work? The cosmology constant, the cosmologist people, they don't care. They don't care about general relativity. That's good because they make a lot of progress. If they care, they just get stuck. I mean, they may stuck for another 30, 40 years. However, they just go ahead and forget about the question. This is a big question. They think this is a philosophical question. They don't have to care. So they forget about that. So all these facts tell you that the correct symmetry for gravitation actually is 3-dimensional diffeomorphism invariant, not 4-dimensional diffeomorphism invariant. And actually this is a gauge theory. Therefore, it can unify with standard model. I mean, this is the important message. Okay, now the rest, if this is time, then you need to have a negative sign here. It's non-trivial. But however, if you look carefully into the so-called Dewitt supermatrix, there's actually one and only one negative mode in the matrix, in the supermatrix. That negative mode can be your time. You understand what my question? I mean, because you need a negative sign. You need a negative sign for the time-like object. So I mean everything is positive. Qij is by definition is spatial matrix positive. So pi ij by definition is corresponding quantity also positive. Definitely. How can you get a negative sign? I mean, how can you get a negative sign for your time variable? Now, marvelous is that the supermatrix actually has negative mode. And one and only one negative mode, and that mode well, you can see that. You can see that the negative mode is coming from here. This is from the supermatrix. So actually, now by looking at now I identify this as my energy instead of calling this energy. Okay. Now, because of this exercise, I identify this as my energy, not this as my energy. That means the corresponding, that means I can factorize this equation. And more important is this at negative sign.
I thought you made a subtraction. You said earlier to make it 0 rather than positive definite. So is that a choice?
No. This is a brute force calculation. This is a brute force calculation. Before I said that, I mean, for example, Chou Ting-dong in his talk, I think 2 years ago in this Taida 60 University of Mathematical Department, Chou Ting-dong gave an opening talk. During the talk, he emphasized this negative sign. This negative sign is the whole bordering, is the whole obstacle to proving positive energy. Why I'm going to say that? Why I'm going to say that is actually this is not an obstacle. If once you identify this object as your energy, you can move this guy to the left side. Then the whole thing left is called energy. It's the Hamiltonian. So that means the Hamiltonian constraint actually is a constraint, but give a dynamical equation for the what? For the definition of the evolution Hamiltonian. Now this is almost trivial, but however, it takes me hours and hours of argument with general relativity experts, including Jim Lester. We have at least more than 100 hours of argument, because he has one of the that's we call a Lester-Witten proof on positive energy.
Okay, so it comes out from a long calculation, but the minus sign is confirmed.
The minus sign is confirmed. It's important that this is minus sign. It's
minus
very
sign
important
here, but in your page 10, it's a plus sign.
No, that doesn't matter. This is this just tell you these are conjugate, these two conjugate variables. Yes, I can look at the next slide. Okay. Now, okay, I know what you mean. Okay, now let's come back to that technical points. But however, this is the same equation as I showed you, right? It's elective side. Now instead of putting a 1 here, I put a general factor beta. If for Einstein gravity, this you just compare. For Einstein gravity, this is equal to the coefficient is equal to 1. But I want to extend, go beyond Einstein gravity. For Einstein gravity, this potential is just r minus 2 lambda. Lambda is the cosmological constant. But I want to go beyond that. So I put a most general coefficient here, and also most general potential here. So I get this equation. Oh, I haven't put the most general. The R still there. I forget lambda. So, but however, then you just all you have to do is to move this guy to left hand side, or you just factorize the equation. And then because of that, you identify this guy as your what? As your energy. So this is the Hamiltonian. So that's how you get your Hamiltonian. Now, come back to George's result. Well, you can easily get it because it's a log Q business. If Q is less than 1, you can extract it, get elective sign easily. So the elective sign is easy. So, but anyway, what I'm going to say is now from the once you release, in Chinese is symbol. You release your symbol. Do not treat this as a Hamiltonian constraint. Instead, you treat this as an equation to extract the energy, to extract Hamiltonian. Then you get a dynamical Hamiltonian for the system. So beta, if beta equal to 1/6 of 1, then you go back to GR, and then if the potential, you can also generate the potential to most general potential. With the most general potential, for example, I can involve dimension 3 operator, dimension 6 operator, so-called quantum tensor. Then the theory becomes normalizable, and then it's low singularidity. I guess, but I haven't proved it. This part is a long way. Anyway, this is just analogous to particle dynamics. So this is Hamiltonian. Now, once I get the Hamiltonian, the most important point, you have to forget about Einstein. For the last 50 years, people keep on talking about Hamiltonian constraint is 0, 0, 0. Then Einstein is a hero, and then they don't want to change anything. But this is almost trivial algebra. But once you list that, once you do that, then amazing thing is the amazing thing is, because they are conjugate variable, that means upon quantization, pi, well, just p or d dx, pi become d delta log q, and then pi bar is just equal to d q bar. And then this projection operator, just the projection operator depends on q, and then to give you the correct coefficient. Now, the whole important point is, once we list that and take one of the factor in this form, then you automatically get a what? Automatically got a Schrodinger equation, or get a corresponding Hamilton-Jacobian equation. Now, it's important. It's very important is this Schrodinger equation is first order in time. You identify this at my time. First order in time. That means what? They have a conserved probability. Now that means that the probability current is positive definite. Now, since John Wheeler and DeWitt, they get this so-called quantum Wheeler-DeWitt equation. It's always quadratic in time. So they never able, in the past 60 years, never able to get a first order in time Schrodinger equation such that the probability current is positive definite. So you have heard about this so-called third quantization. Try to get around of this question. But however, by this simple, once you release your symbol, the devil in your mind, then everything becomes so nice, work out so nice, so trivial. Now, so from now on, my evolution will be respect to my h bar Hamiltonian, where h bar is written over here. Okay. Now, so let me. For given any initial data, from that I can construct delta log Q, and then I can evolve with my Hamiltonian, and then subject to this momentum constraint. And then now the difficult part is you get a theory, you get an equation of motion. Einstein's theory has been proved working very well, both at solar scale, at galactic scale, and also at cosmological scale. That means somehow you have to reproduce Einstein's equation, Einstein's physical content, or reproduce Einstein's equation of motion. How to do that? Now, this is a little bit technical, but however, you look at Einstein's equation from the left point of view, and then this is called Einstein equation, and then the evolution in coordinate time. In Einstein equation, in coordinate time is just equal to d dq dt equal to this object, and then this canonical momentum here is related to the so-called second fundamental form of extrinsic curvature, like this. So if I take trace on both sides, I got this equation. That means if I identify my n here, the left function here, equal to this block, then I reproduce. Then this equation will be identical with the equation with the equation motion generated by h bar. That's I want to. Well, I'm not going to cheat you, but I mean you can work in detail. I work out the details, and then because they have the same equation of motion, then maybe I need one more physics over here. Okay. What does this kinetic? Okay. Now, this is called extrinsic curvature. What's extrinsic curvature? Extrinsic curvature is, for example, I embed my arm in the four space-time. Then the normal component is changed on the surface, right? This extrinsic curvature, that means if I have an object like this and I have an object like this, then I cannot put this together to form what? To form a space-time. In order to form a space-time, the extrinsic curvature has to match. This is an extra condition to allow us to identify our equation of motion with Einstein's equation of motion. And then because the equation of motion is the same, so therefore the physical content is the same. So then this theory, we produce all the theory of Einstein, or all the result Einstein has produced. This is the important point. So, for example, given you a particle, how do you know this is a particle trajectory? Well, for a particle trajectory, that means at every point along the trajectory, the momentum is well defined. So this is exactly the physics of extrinsic curvature. That means in order to stack up all these free space to form a force space, that the extrinsic curvature must be matched. And then in order to match the extrinsic curvature, then the left function must be chosen in such a form like this. And then if you chose the left function in form like this, then you just reproduce, just algebraic check and reproduce the Einstein equation. And therefore we produce everything what Einstein has reproduced. But, however, in the Einstein equation, because you have a Hamiltonian constraint, so n is a Lagrangian multiplier. Here, n is fixed. If we view the physical meaning of the left function and its relation to intrinsic time, n is the left function, and then it is related to the what? It's related to this log Q time. So from that, once I get n, I plug it in, I get my ADM space-time. Let me don't spend too much time on this left function, because you guys may not be interested in this, to understand the left function, because this is very technical already. What I'm saying is, by matching the extrinsic curvature, I can reproduce all the Einstein physical content. So. Now, this is another miracle. The log Q time I identify cannot be a time. Or in the community, in the language of GL community, it's multi-finger. Because log Q, although you have a nice looking evolution equation here. No, sorry, this nice looking evolution equation. But you cannot integrate it. Because why? Because this depends on x, it's path dependent. That means this equation in some sense is useless. Well, which makes sense because what? Because the determined Q, the matrix is a field. The field component has infinite degree of freedom. Saying your determinants make out of the field degree of freedom, which are also of infinite degree of freedom, bear infinite degree of freedom. So now the hard part is what? The hard part is to collapse this. On this side is infinite degree of freedom. We collapse this into single parameter, h. Because time is a single parameter. You have the 1 second, 2 seconds, 3 seconds. It's a single parameter. You cannot use an infinite degree of freedom field variable to parameterize time. That's meaningless. But technically, that means you cannot integrate the equation. So, but however, there's a so-called Hodge decomposition. Hodge decomposition means what? Any vector you can decompose into the what? Into the divergence past what? Past curve, and then past invariant path. So this is just, so I can do the same thing, do the decomposition here, and then I can use the gauge freedom in the momentum, remove the gauge dependence. So that means after Hodge decomposition, the delta log Q time, which of infinity degree of freedom, will collapse in the single parameter delta H. That will become your real time. Well, that can be really identified time. I think this is the root of the world of gauge. Why the world is gauge. Without gauge theory, you cannot. There's no way you can collapse on the right